Hi.
Good morning, everyone. We will commence shortly. We are giving a couple of minutes so everyone can attend our first webinar. Thank you very much. Good morning. We want to begin by thanking you for subscribing to this webinar. We were giving a couple of minutes for everyone to be able to join us. This webinar is the first of our CondaLab talks. This concept refers to the webinars we will prepare for you from time to time on diverse subjects of interest, such as food or water safety, to mention a few. This CondaLab talk is also the first one of the food safety series. Without further ado, it is a pleasure to welcome you all, and the purpose of this CondaLab talk is to discuss one of the most important indicator microorganisms in the food industry, Campylobacter, as well as to review the reference method so you are familiar with it. We want to keep it dynamic, so we encourage you to participate and send any questions, doubts, or information requests on the questions box. You have it on your right. And we will answer these at the end of the webinar. So let's begin. To start, we will introduce briefly Campylobacter species and Campylobacteriosis, the bacteria, and the disease. The genus Campylobacter belongs to the family Campylobacteriaceae. Campylobacter species are gram-negative, spiral-shaped or curved rods with a single polar flagellum, bipolar flagella, or no flagellum at all. Members of the genus Campylobacter are non-spore-forming bacteria and grow under microaerobic conditions between 30 and 42 degrees Celsius, the maximum being 45 degrees Celsius. Currently, the genus Campylobacter unifies 17 species and 6 subspecies, of which the most frequently reported in human diseases are Campylobacter jejuni and Campylobacter coli. Both species are zoonotic pathogens with wide host ranges, including farm animals such as cattle, sheep, pigs, and poultry, and wild animals as well. Campylobacter can also be classified into microaerophilic and anaerobic, being jejuni a classical bacterium that conforms to the first category. Microaerophile refers to those adapted to particular environments that contain low oxygen concentrations. Therefore, fully aerobic conditions are growth inhibitory. Campylobacter species are responsible for campylobacteriosis, a foodborne zoonotic disease. So, why is campylobacteriosis relevant? It is considered the most common bacterial cause of human gastroenteritis in the world, as well as one of the 4 key causes of diarrheal disease. In the European Union, campylobacteriosis is the most reported zoonosis in humans since 2005, with almost 250,000 cases reported every year. The onset of the disease symptoms usually occurs 2 to 5 days after infection with the bacteria, but can range from 1 to 10 days. The most common clinical symptoms of Campylobacter infections include diarrhea, frequently bloody, abdominal pain, fever, headache, nausea, and/or vomiting. The symptoms typically last 3 to 6 days. Death from campylobacteriosis is rare and is usually confined to very young children or elderly patients, or to those already suffering from another serious disease such as AIDS. Complications such as bacteremia, which is presence of bacteria in the blood, hepatitis, pancreatitis, and miscarriage, have been reported with various degrees of frequency. Post-infection complications may include reactive and neurological disorders, such as Guillain-Barré syndrome, a polio-like form of paralysis that can result in respiratory and severe neurological dysfunction in a small number of cases. When talking about the sources of the disease, a third of the cases come from raw poultry meat because Campylobacter lives in the intestines of healthy birds. The most common source of campylobacteriosis is undercooked meat and meat products, along with raw or contaminated milk, and also contaminated water or ice. Given campylobacteriosis wide occurrence, this hinders the development of control strategies throughout the food chain. To visualize the importance of Campylobacter, we are looking at a chart from the European Union One Health 2018 Zoonosis Report, which was published last December. In 2018, campylobacteriosis was the most commonly reported zoonosis, as it has been since 2005, representing alone almost 70% of all the reported cases. Campylobacteriosis was followed by other bacterial diseases such as salmonellosis, staph infections, and yersiniosis, in being the most frequently reported. But even these 3 summed up aren't as high as campylobacteriosis. Therefore, its importance and relevance is clear. We will discuss now some of the European Union regulations that are currently in place. Directive 2003/99/EC is for the monitoring of zoonosis and zoonotic agents. But for better reference, zoonosis refers to diseases and infections transmissible directly or indirectly between animals and humans, and zoonotic agents to bacteria, fungus, or other communicable disease agent that can cause substantial morbidity mortality, or are even difficult to diagnose in animals. One of the directive objectives is to identify zoonotic agents that need to be monitored, including Campylobacter, as well as the collection of data on the occurrence of zoonosis and zoonotic agents in animals, food, feed, and humans, which is necessary to determine the trends and sources of zoonosis with the assistance of the Community Reference Laboratory for the Epidemiology of Zoonosis. Moving on to the next regulation, we have the Commission Regulation 2017-1495 regarding Campylobacter in broiler carcasses that indicates the microbiological criteria, the specific hygiene requirements, as well as hygiene criteria, which set indicative contamination values above which corrective actions are required in order to maintain the hygiene of the process in compliance with food law. The European Food Safety Authority, or EFSA, studied the prevalence of Campylobacter in broiler carcasses and concluded that 75.8% were contaminated. The limit of 1,000 colony-forming units per gram comes from the EFSA estimation that a public health risk reduction from the consumption of broiler meat of more than 50% could be achieved if only carcasses complied with this limit, and highlights that significant different contamination levels exist between neck skin and breast skin samples. The regulation also indicates that the international standard ISO 10272-2 is the method for the enumeration of Campylobacter in food and feedstuffs. It should, therefore, be laid down as a reference method for verifying compliance with the criterion for Campylobacter in poultry carcasses. The sampling rules, guidelines, and sampling frequencies are also specified in the regulation. Since meat is the main source of Campylobacteriosis, we will overview quickly the meat industry. Here on the left, we have a pie chart with 2017 data from the Food and Agriculture Organization of the United Nations, or FAO, of the world meat output. As we can observe in blue, pig meat is the principal produced meat, followed by poultry in purple, which, as we've mentioned before, is the main concern when talking about Campylobacter. In third place, we have bovine meat, and lastly, ovine meat with a small percentage. Now that we have a global view of what is being produced, let's review our consuming habits. This column chart was obtained from an OECD, the Organization for Economic Cooperation and Development, and FAO publication that provides market projections for major agricultural commodities, specifically for the period in 2017. At a glance, it is perfectly clear that in most regions, the main consumed meat is poultry, again in purple, which makes sense by being the second most produced. This information consequently enhances the importance of Campylobacter control in this industry. And since the importance of controlling Campylobacter has been established, we will review in detail the ISO method for the detection and enumeration of Campylobacter species ISO 10272. This method has two parts. Part 1 is for the detection method by enrichment or direct plating of Campylobacter species, and Part 2 for the enumeration of Campylobacter species by colony count technique. Depending on the type of sample and the purpose of the test, 3 different detection procedures can be used, and we will review each one of them. All the products indicated are available in Conda's catalog and are highlighted in bold. If you'd like more information about our products, please contact your area manager or visit our website at www.condalab.com. First, we will discuss the detection procedure by enrichment in samples with low numbers of Campylobacter and low level of background microflora, and also perhaps with stress Campylobacter, for example, in cooked or frozen products. Starting with the selective enrichment, 10 grams or milliliters of the sample are added to 90 milliliters of a liquid enrichment medium, the Bolton selective enrichment broth. The incubation conditions are at 37 degrees Celsius in a microaerobic atmosphere for 4 to 6 hours, and then at 41.5 degrees Celsius for 44 hours. For the enrichment culture obtained, 2 selective solid meal are inoculated in the presumptive isolation phase. Campylobacter agar-based blood-free, or CCDA, and any other solid selective Campylobacter medium, with different selective principles from those in CCDA, for which Campylobacter agar-Preston is adequate. The incubation conditions are at 41.5 degrees Celsius in a microaerobic atmosphere and examined after 44 hours to detect the presence of suspect Campylobacter colonies. In result reading, typical colonies are grayish on CCDA agar, often with a metallic sheen, and are flat and moist, with a tendency to spread. Colonies tend to spread less on drier agar surfaces. Other forms of colonies may occur. The suspect Campylobacter colonies are examined for morphology and motility using a microscope and confirmed by detection of oxidase activity. The selected colonies have to be subcultured onto Columbia agar, incubated in microaerobic atmosphere at 41.5 degrees Celsius for 24 up to 48 hours. At the same time, an aerobic growth test on Columbia agar must be incubated at 25 degrees Celsius aerobically for 44 hours and examine the plate for absence of growth of colonies, because, as we've previously discussed, Campylobacter species are either anaerobic or microaerophilic. Optionally, the Campylobacter species can be identified by specific biochemical tests and/or molecular methods. The next detection procedure by enrichment is for samples with low numbers of Campylobacter and high level of background microflora, for example, as in meat or raw milk. The procedure is very similar to the previous we have reviewed. The difference is that 10 grams or milliliters of the sample are added to 90 milliliters of a liquid enrichment medium, in this case directly onto Campylobacter Preston broth. The incubation conditions are at 41.5 degrees Celsius in a microaerobic atmosphere for 24 hours. From the enrichment culture obtained, only the Campylobacter agar-based blood-free, CCDA, is inoculated. The incubation conditions are at 41.5 degrees Celsius in a microaerobic atmosphere and examined after 44 hours to detect the presence of suspect Campylobacter colonies. It must be mentioned that in all detection procedures, both steps, result reading and confirmation, are the same as in the first procedure. The suspect Campylobacter colonies have to be subcultured onto Columbia agar in microaerobic and aerobic conditions and examined for morphology and motility. And lastly, confirmed by detection of oxidase activity. Once again, optional methods for identification of a species are biochemical tests or molecular methods. The third and last detection procedure, by direct plating, is for samples with high numbers of Campylobacter. This procedure can be used in combination with ISO 10272-2 in order to count number of Campylobacter per gram, per milliliter, or per square centimeter in the test material. Here, the enrichment technique is not used. The sample is plated directly or after suspending in an appropriate amount of liquid onto Campylobacter agar-based blood-free, CCDA. The incubation conditions are at 41.5 degrees Celsius in a microaerobic atmosphere, and examined after 44 hours to detect the presence of suspect Campylobacter colonies. Typical colonies are once again grayish on CCDA agar, often with a metallic sheen, flat and moist. And as we've indicated previously, both steps, result reading and confirmation, are the same as in the previous procedures. The suspect Campylobacter colonies have to be subcultured under Columbia agar in microaerobic and aerobic conditions, examined for morphology and motility, and lastly confirmed by detection of oxidase activity. Specific biochemical tests and molecular methods are optional. With the review of the ISO 10272 method, our presentation ends. So now we will begin answering the questions and doubts you have been submitting during the webinar so far. I would like to introduce my colleague and product manager, Jaime Martinez.
Okay, hello everybody. I'm Jaime, product manager for microbiology. So we are going to answer some questions that we have. One from Anel from Finland. Okay, she asked about. Let me check. Sorry, the question. Okay. Annie from Finland said, are there any other selective media that can I use for Campylobacter isolation? Well, as reference methods always indicate the CCDA as selective method, but other agar can be used. There we can find Carmali agar that was in the last review ISO was indicated as selective media. Also Carmali agar. Another one is Butler, for example. But anyway, this is a laboratory decision that they have to indicate and verify what kind of agar they have used. The choice and the possibilities are depending on the selective agent on this way. Okay, so definitely it's a laboratory decision. Always they have to check the performance of the methods and be compliant with the regulation for productivity and the selective action. Okay, I have other question from Italy. She's Antonella, and she's asking about what kind of microbiological control they have to do to the media. Okay, if everybody knows, all the microbiological control are indicated in other ISO. This ISO is 11133. Is the reference method for productivity and performance media. In this ISO, we can find all the control media that we have to do to our culture media in our method. Okay. For example, also in our TDS, in our technical documentation, all the control, the microbiological control are following this ISO. So we have to check the productivity and the performance for Preston and Bolton broth, and also for CCDA. For example, regarding for the first question, these secondary selective media are not indicated there. So you have to follow the commercial instruction for the manufacturer. Okay. At the moment, we don't have more question about it, Aletia. So maybe if anyone is asking for other one, we will able to answer for email, of course, or if you can contact with your sales representative or directly for the micro@condalab.com is our email for solve and answer any doubt that you can have about Campylobacter or whatever other kind of matters regarding to microbiological products from CondaLab. Okay, so from my point of view, we don't have more questions. I hope that everything is clear. So Aletia, we can conclude and say goodbye.
Yes, I think these are all the questions we have. I believe we had one more. Which are the main advantages about studying Campylobacter with culture media against PCR methodologies?
Okay. The advantage on this way is, as always, that you detect a Campylobacter with the reference method, you are complying the regulation. So all the auditories process will be easier to get all accreditation if you are following the detection methods. Sometimes also you have some problem if you don't have experience working with PCR or molecular methods. Sometimes the contamination process, cross-contamination is very common to find on this kind. So many times also, of course, the investment that laboratory needs to put all this kind of techniques is much higher than detection for culture media. So many times it's much better always, that with technical, molecular technical methods, if you have a positive, you have to check with a traditional method there. So many times also other points are quantification, because sometimes quantification by molecular methods are able, it's a little bit more difficult to find a correct data in the exact data that's a traditional one.
Okay. And I think we have one more just to end. It's clear that Campylobacter is having more and more resistance against antibiotics. Would it have an impact in the ISO study protocols and methods?
Okay. Yes, of course, because the antibiotic resistance, of course, is a global awareness of this way in this moment. So in this moment, the beta-lactamides are the selective agents that this method reference are applying. At the moment, there is not a huge problem with the resistance for Campylobacter. I think that is more in consequence that all bacteria, not only Campi this way. Of course, as you know, always ISO methods are reviewing, are studying and updating on this way. For example, just a few years ago, 2 years ago, a new review for this ISO was launched. So ISO committee are always improving and adapting this method to the real situation on this way. I don't have any notice at the moment that they are working in the resistance and the influence of antibiotics in Campylobacter, but of course, you know that many farms and many production sites are giving a huge quantity of antibiotic in order to reduce and decrease the mortality in the farm, and there is a huge use, but it's a problem concerning all kind of bacteria, not only Campylobacter. But as I said, ISO committee are always adapting or review every methods, every ISO normative.
Perfect. So I believe those are all the questions that have been answered. And we, once again, would like to thank you for attending our first webinar. We hope you found it useful and that you are now familiar with the ISO method for the detection of Campylobacter. So we hope to see you in the next one. Thank you all.
Thank you. Bye-bye.